Frugality. We now turn to a radically different class of problems, in which the auctioneer is a buyer intent on hiring a team of agents to perform a complex task. In this model, each agent I can perform a simple task at some cost VI known only to himself. Based on the agent's bids BI, the auctioneer must select a feasible set, a set of agents whose combined skills are sufficient to perform the complex task. Xi equals to 1 if agent I is selected, and pay each selected agent some amount, Pi. This is negative because we previously defined Pi as a transfer from the agent to the auctioneer. The setting is thus defined by the set system of feasible sets ES, where E represents the set of agents and S represents the collection of feasible subsets of E. In terms of our single parameter framework, we have C of x equals to 0 if the set I such that xi equals to 1 is in S and infinity otherwise. Several special cases have received a great deal of attention. Example 13.50. Path auctions. Here the agents own agencies of a non-directed graph, i.e. E is the set of agencies, and the auctioneer wishes to purchase a path between two given nodes S and T, i.e. S is the set of all ST paths. Example 13.51. Spanning tree auctions. Here the agents own agencies of a non-connected, undirected graph, so again, E is the set of agencies, and the auctioneer wishes to purchase a spanning tree. Whereas when the auctioneer was a seller, our goal was to design a mechanism to maximize his profit. Here our goal is to design a mechanism to minimize the payments the auctioneer makes, i.e. to hire the team of agents as cheaply as possible. Hence, analyzing the frugality of a mechanism, the amount by which it overpays, becomes an important aspect of a mechanism design, analogous to profit maximization. We study frugality here using worst-case competitive analysis, as in section 13.4. The first observation is that here, unlike the digital goods auctions we focused on in the previous sections, the auctioneer is interested only in a single object, a feasible set. Thus, at very high level, these problems are closest in spirit to the single item auction that we discussed in the context of profit maximization. For single item auctions, in the absence of any prior information about agents' valuations, it is possible to show that the victory auction is optimal and of course achieves a profit equal to the value of the second highest bidder. Thus, a natural first mechanism to consider for hiring a team auctions is the VCG mechanism. Consider a path auction where the graph consists of unparalleled agencies from S to T. This corresponds exactly to the case where the auctioneer is buying a single item, and the victory mechanism will result in a payment equal to the cost of the second cheapest edge. Compare this to what happens in a graph consisting of two vertex disjoint ST paths P and P prime, each with n agencies. Suppose that each edge on path P has cost 0, and each edge on path P prime has cost 1, so that the total cost of path P is real and of path P prime is n. Then the VCG mechanism will purchase path P, and each edge on that path will be paid n, for a total auctioneer payment of m squared. Thus here the VCG mechanism pays much more than the cost of the second cheapest path. Can we do better? How, in general, does the optimal truthful mechanism in terms of competitive ratio depend on the combinatorial structure of the set system?